In this video tutorial, I will show the fundamental machine learning concepts for total beginners in this field. I will show the machine learning the way I would like to be taught when I started my machine learning journey. This video tutorial contains theoretical aspects of machine learning and practical part as well. How do machines perceive the world? Part 2. Day 2. Why everything becomes a number. Learning objectives. Learn the gradient descent method, following the slope. Learn about gradient explosion and vanishing problems. Master basic normalization techniques. Gradient descent, following the slope. Using derivatives in gradient descent. Gradient descent is an optimization algorithm that uses derivatives to find the minimum of a function. It works as follows. Gradient isn't simply the derivative or partial derivatives in the case of multiple variables. The derivative indicates the slope pointing in the uphill direction. We want to go downhill, so we move in the opposite direction to the gradient. We take small steps, their size controlled by the learning rate. Update rule. In a simple form, it's xnew equals xold minus learning rate times derivative, which is xnew equals xold minus alpha times f prime of xold, where alpha is the learning rate step size. Why the negative sign? The derivative points in the uphill direction, the direction of function increase. The goal is to minimize error, so we move downhill in the opposite direction. If derivative is greater than 0, function is increasing, we should move left, decrease x. If derivative is smaller than 0, function is decreasing, we should move right, increase x. If derivative equals 0, function is at a minimum or maximum point. The problem: when gradients behave incorrectly. After understanding derivatives and gradients, we can see why feature scaling is crucial. Consider a loss function dependent on two features. L of x1, x2 equals x1 squared plus x2 squared. The partial derivatives are partial derivative of L divided by partial derivative of x1 equals 2 times x1, and the partial derivative of L divided by partial derivative of x2 equals 2 times x2. If x1 is 0.001 and x2 equals to 1000. Gradient for x1 equals then 0.0012, very small. Gradient vanishing. Gradient for x2 equals then 2000, very large. Gradient explosion. A learning rate that works correctly for x2 will be too large for x1 and vice versa. Source code. The problem when gradients behave incorrectly. Using NumPy, import NumPy as NP. Using matplotlib, import matplotlib.pyplot as plt. Visualization of gradient problems. Using the subplots object-oriented method plt.subplots, and it returns figure and 3 axes for 3 different plots: vanishing gradient, stable gradient, and exploding gradient, and setting the random seed to 42 to have the same results. Each plot will be set up constructed in the same way. Histogram with title, X label, Y label, and containing gradients with teeny data, normal data, and huge data. Each of the plot is from subplots, vanishing gradient in here, stable gradient in here, exploding gradient in here. Gradients are just the derivatives, and in here we have 2 times any data, so it's from x squared. Data t-SNE is from random rand n, which is shift tab on it, return a sample or samples from the standard normal distribution. So in this case, data t-SNE is times 1e minus 6, which is around 0.00001 super small number. And for data normal, it's just rand n for 100. And for the huge is as well rand n, but times 1e6, which is a number around a million. So to show the plots, at the end plt show, and to run the code, simply shift enter, wait for a while, and we have vanishing gradients, stable and exploding gradients. They look similar, but they aren't. So we can ask a question, why can't we see the problem? First thing, histograms doesn't properly show scale differences between subplots. Each subplot automatically rescaled its own x-axis. This means around 0 on the left and around 2 millions on the right occupy the full width of the plot. Second, as a result, all 3 histograms look like normal distributions. Third, but if we look at the axis labels, left histogram x-axis around plus minus 1 times 10 to the minus 6th power. Middle histogram x-axis around plus minus 5. Right histogram x-axis around plus minus 5 times 10 to the 6th power. So the correct answer for why can't we see the problem? Gradient spread increased by 12 orders of magnitude. So what do the histograms show? Left vanishing, gradients clustered around 0, around plus minus 2 times to the 10 to the minus power, which equals 0.00000 super small value. They looked flattened and stuck to the 0, so learning process extremely slow. So the middle histogram, stable, gradients are centered around 0, but spread in the range approximately -4 +4. This is healthy, neither too small nor too large value, the green one. The right histogram, exploding gradients. Gradients reach values in the millions, plus minus 2 times 10 to the 6th power, around 2 millions. The bars look tall in the middle because the histogram compresses the scale, but numerically the gradients are huge and unstable. Most common derivative rules in machine learning. Most frequently occurring derivatives. Below are the most common derivatives in machine learning. On the left column, function f of x. On the right column, function f prime of x. Function f of x equals c constant. Derivative f prime of x equals 0. Function f of x equals x. Derivative f prime of x equals 1. Function f of x equals x to the n power derivative f prime of x equals n times x to the n minus 1 power. Function f of x equals e to the x power derivative f prime of x equals e to the x power. Function f of x equals natural logarithm of x derivative f prime of x equals 1 over x. F of x equals sine of x derivative f prime of x equals cosine of x. And f of x equals sigmoid of x derivative f prime of x equals sigmoid of x times 1 minus sigmoid of x. Chain rule, the most important rule. For complex functions, the chain rule is used. If y equals f of g of x, then derivative of y divided by derivative of x equals f prime of g of x times g prime of x. This is crucial for backpropagation in neural networks. Source code. Most common derivative rules in machine learning. Using NumPy for numerical operations, I will show how the derivatives looks like for constant, linear, power, exponential, logarithmic, and sigmoid. To run the code, I will simply hit Shift Enter, and we have it. So for constant f of x equals 5, the derivative will be equals 0 no matter what value we pass. For linear function, f of x equals 3x, the derivative will be always 3 because this is the slope and the derivative is the rate of change. For the power function, f of x equals x squared, the derivative will be 2 times x, and we double the value we pass. So the output is 4, we passed 2. Partial derivatives, multiple features, multiple gradients, functions of multiple variables. In machine learning, we rarely work with just one feature. Models typically have multiple inputs, which means we need to use partial derivatives. Derivatives calculated with respect to one chosen variable while treating the others as constants. Notation, symbol, partial derivative instead of total derivative. Expression, partial derivative of f divided by partial derivative of x means how does f change when only x changes. Mathematical example. Consider a function of two variables, f of x, y equals x cubed plus y squared. The partial derivatives are partial derivative of f divided by partial derivative of x equals 3 times x squared plus 0 equals 3 times x squared simply. Partial derivative of f divided by partial derivative of y equals 0 plus 2y, which is simply 2y. Notes. When calculating partial derivative of f divided by partial derivative of x, variable y is treated as a constant. So y squared equals 0 simply disappears. When calculating partial derivative of f divided by partial derivative of y, variable x is treated as constant. So x cubed equals 0 simply disappears. Understanding partial derivatives with real estate price example. Example without code. Partial derivatives can be illustrated through a simplified real estate valuation model. Let's assume we have unrealistic but mathematically simple price function. F of bedrooms, area equals bedrooms cubed plus area squared. This means price depends on the cube of the number of bedrooms and the square of the area in square meters. Determining partial derivatives. Partial derivative with respect to number of bedrooms, which is partial derivative of price divided by partial derivative of bedrooms equals 3 times bedrooms squared, meaning shows how much the price will change when the number of bedrooms changes, assuming constant house area. For a house with 2 bedrooms, the rate of price change is 3 times 2 squared equals 12 units per bedroom. Partial derivative with respect to area, which is partial derivative of price divided by partial derivative of area equals 2 times area, meaning shows how the price will change when the area changes, assuming constant number of bedrooms. For a house with area 2000 square meters, the rate of price change is 2 times 1000, which is equals 2000 units per square meter. Gradient interpretations. Partial derivatives are rates of change. They show price sensitivity to each feature. They indicate which feature has greater impact at specific values. Example interpretations. For a house with 3 bedrooms, partial derivative of price divided by partial derivative of bedrooms equals 3 times 3 squared equals 27. Adding one bedroom increases price by about 27 units. For a house with area 1500 meters squared, partial derivative of price divided by partial derivative of area equals 2 times 1500, which is 3000. Adding 1 square meter increases price by about 300 units. So, scale problem warning. The gradient for area in meters squared is much larger than the gradient for number of bedrooms. Even though both features may be equally important, this exactly shows why normalization is necessary. Source code. Understanding partial derivatives with real estate price example. I will be using NumPy for numerical operations. The price model is function f of bedrooms, area equals bedrooms cubed and area squared. The example house 3 bedrooms and 20 square feet in hundreds of square feet to make numbers easier. Calculate the price using the price model above. Partial derivatives. The partial derivative of bedrooms is simply 3 times bedrooms squared because we had bedrooms cubed. And partial derivative for square feet is simply 2 times square feet because the area was squared. And then printing the calculated values and some interpretations. To run this code, I will simply hit Shift. So the output shows the price model, the house and the price, and the partial derivatives. So the partial derivative for bedrooms is 27 units, the partial derivative of area is 40 units, and adding one bedroom, price increases by 27 units. Adding another 100 square feet increases price by 40 units. Key conclusions. Partial derivatives. In gradient descent, both parameters are updated at the same time using their respective partial derivatives. So, bedrooms new equals bedrooms old minus alpha times partial derivative of price divided by partial derivative of bedrooms. And the area new equals area old minus alpha times partial derivative of price divided by partial derivative of area, where alpha, learning rate, is the same for both parameters. However, if one partial derivative is 1000 times larger than the other one, due to differences in feature value scales, a problem arises. This is exactly the main need for using normalization. Key conclusions. Derivatives. Derivatives measure the rate of change, telling us how to adjust parameters. Gradient descent follows the opposite direction of the derivative to find the minimum. Large features values generate large gradients, leading to learning instability. Small feature values cause very small gradients, resulting in slow learning process or lack thereof. Normalization makes gradients have similar scales, enabling stable learning. One learning rate can work correctly for all normalized features.